to all and welcome to this lecture. We are in module 10, lecture number 2. In this lecture, we will discuss about band-to-band tunneling, GIDL and some quantum effects. So, in this lecture, we are going to discuss some second order effects which we ignored when we were discussing about long channel devices. Out of which we will discuss here about quantum mechanical effects, band-to-band tunneling, gate induced drain leakage or called GIDL, and components of leakage current which is available in short channel devices. These are the learning outcomes of this lecture which helps you to understand the physical origin of band-to-band tunneling which occurs at heavily doped source and substrate junction. Similarly, this will also help you to understand the phenomena of GIDL, that is gate induced drain leakage. In this lecture, we will discuss about quantum mechanical effect which occurs at the surface, which we simply ignored when we were talking about long channel devices. So, let us get started with a quick recap. In previous lecture, we were discussing about DC gate current. We said that if the thickness of the oxide is larger, then the electron which is confined here will not find a path to move, because in this side there is a thicker oxide and in this side the conduction band bending of the silicon. However, when the oxide thickness is narrower, there is a finite probability that this electron will tunnel through the oxide and give rise to a gate to channel current. We have discussed about this component in terms of MOSFETs based on the terminal voltages like VDS and VGS. If you apply significant amount of VGS, then there is a significant amount of gate to channel current which constitutes in two parts. One is IGS and IGC. So, this current IGC is dependent upon the number of charge present in the inversion layer as well as the electric field in x direction and the probability of tunneling. Thus, if we find out the total number of inversion charge near the source is more, and hence the current contribution IGC or IGS will be more. If the current density at the drain side is more, then the contribution of IGD will be more. We have also discussed that when you increase VDS, the gate to drain voltage is reduces, and because of that IGD found to be saturated when you increase VDS. Now, let us see the other second order effects which we simply ignored when we were discussing about the long channel devices, out of which the first is quantum mechanical effect. So, if you see the same band diagram, like this is an oxide and let us say you have applied some field. So, there is a bend bending, the electron is confined in this region which we called it as triangular potential well, triangular potential well. The electron which is residing in triangular potential well, then it constitutes a current when you apply the terminal voltage between source to drain. So, in our analysis what we considered is the sheet of this charge present very near to the source. The sheet of this charge is present very near to the surface. However, when the electron confined in a triangular potential barrier, then this is not correct, because the electron wave function when it is confined, it shows that the maxima is somewhat away from the surface. Let us consider this distance is dm. So, the first thing we simply ignored when we were talking about small channel, when we were talking about long channel device, that the surface of a infinitesimal thickness is present very near the surface. However, this is not the actual case. When the electron confined in the triangular potential well, it is present somewhat away from the surface of distance, let us say dm. If the charge is present away from the surface, meaning the capacitance here is decreases, and hence you can simply say the gate does have a poor control in this charge, right. Thus, you need to model in such a way that this dm factor should be incorporated. The second quantum effect we simply ignored is the band gap widening. So, when you go for a quantum effect and you find that the electrons are confined in a triangular potential well, then the band energy is not continuous. It will split it into sub bands, and hence the effective band gap is slightly increased. Thus, the electron requires more energy to move from valence band to conduction band because of effective increase in the band gap. This actually decreases Ni, which in turn decreases the Fermi potential, and which in turn increases the threshold voltage. So, these two factors we simply ignore when we were talking about the long channel devices. However, we need to take care about these effects. Now, how can we incorporate these things in our modeling approach with simple approximations? The first thing is, let us incorporate the effect of dm, right. For that, we will consider that this is surface and our sheet of charge is present dm distance away from the surface. So, still we are considering the inversion charge is having a sheet, but it is away from dm. So, ultimately this will increase the effective oxide thickness, which is can be given by the change in effective oxide thickness is equals to epsilon OX into dm divided by epsilon S. So, using the concept of effective oxide thickness or in terms of capacitance, we can include the effect of dm in our calculation. However, strictly speaking, this is simply an empirical approach. It is not, it will not give you an accurate results because it requires quantum mechanical modeling, which we are not going to discuss in this course. If you wish to find dm, then using quantum mechanical approximations, we can simply calculate dm, which is a function of bulk charge as well as inversion charge. Here these factors are fitting parameters like B1, and these are constant 11 by 32 and minus 1 by 3. So, by doing this, you can calculate the effective change in the capacitance and incorporate in our model to preserve the credibility of the model what we have derived for long channel devices. The second effect is the increase in threshold voltage. So, as we have discussed that the bands in the triangular potential barrier is now sub bands, and hence it will increase the effective band gap, and because of the increase in effective band gap, Ni decreases, which means the Fermi potential decreases, which means you have to apply a more effort to increase the same amount of inversion charge. It means the threshold voltage increases. So, we can simply model the threshold voltage by incorporating an additional term, that is delta phi naught, in terms of surface potential. So, when you go for a modeling, then you need to incorporate this additional delta psi naught in your threshold voltage equation to model this effect. So, we can simply rewrite a new equation for threshold voltage, that is change in threshold voltage is delta phi naught plus gamma times of phi naught plus delta phi naught minus square root of phi naught. Again, it requires quantum modeling to calculate what is delta phi naught. So, using different modeling approach, we can find out what is the change in delta phi naught or phi naught requires to add in the threshold voltage equation, such that the effective threshold voltage will increase because of this quantum mechanical effect, right. So, we can say the quantum effect increases with higher transverse field, thinner oxide and lower inversion charge thickness. This effect is found strong near the drain, near the source end, and weak near the drain end, though it should be available in practice throughout the channel, but found strong near the source end. So, we can ignore these effects near the drain end. It is negligible in weak inversion and it is significant in strong inversion. So, it is important to include these effects when you model for strong inversion equation. Now, let us see what is junction leakage in scale MOSFET. If you see the MOSFET, we do have junctions, that is the junction between body and drain and the junction between body and source. So, this is source, this is drain. Here this junction is nothing but a PN junction because body is of P type. If the doping of the substrate is high, let us say of the order of 10 to the power of 15 or 10 to the power of 18 per centimeter cube, in that condition this forms a depletion region narrower. If the depletion region is narrow in a PN junction, then the field in that region is very high. So, we can understand by a band diagram, suppose you have a P region here which is like this and N region here which is like this. So, PN junction band will look like this. Now, when you reverse bias this PN junction, what will happen? This will look like this, right. So, this is P side, this is N side. Here you do have filled valence band and empty conduction band. The same scenario is happening here. If you do have substrate is heavily doped, even if it is not heavily doped, you do have a depletion region here and it can be considered as one sided PN junction. Because of that, what will happen? There is a bending. Now, if you increase VDS, meaning what you are doing, you are making it reverse bias. So, if it a reverse bias, then the bending will look like this. Now, if the substrate doping is higher, then there is a finite chance that the tunneling will occur from one band to another band, because the basic conditions for tunneling is the tunneling barrier should be steep enough or abrupt. The second is there should be a filled band at one side and empty band at other side, meaning these two criteria fulfilling here, which shows that if you apply a voltage VDS, this junction becomes reverse bias and hence there is a finite chance that the electron will tunnel from P side valence band to N side conduction band. This is same as the electron will tunnel from this side to this side. So, the electron, the newly tunneled electron will reach the drain, and similarly the newly tunneled hole or the hole is created because of tunneling of electron is here. Now, you have a body connection which is either negative or 0. If you connect VSB, it is negative. So, this hole will give you what? Drain to body current. The same concepts what we have discussed when we were discussing about this will give you drain to body current, and this electron will follow the same stream of electron which is coming from the source and constitute the current drain to source, right. Now, the band to band tunneling current is basically depend on what is the field present at the junction. So, in general IBT/BT band to band tunneling can be given by ABT/BT into VR into E max into exponential of minus BT/BT divided by E max, where VR is the applied reverse voltage, E max is the maximum electric field at the junction, right. ABT/BT and BBT/BT are the constants, where ABT/BT is directly proportional to the junction area, correct, where which the tunneling happens. So, the concept of this band to band tunneling will apply in MOSFET junctions and see what will happen. That will give you an idea about gate induced drain leakage. Let us consider we do have a MOSFET and we are only considering the drain side and channel side, because in general the source side is kept at 0 volts. So, the tunneling will happen when there will be a reverse bias and the doping will be higher. So, let us consider a simple operation when VDS is kept low and you are applying a positive gate voltage. if you apply a positive gate voltage, because of single positive Q charge at the gate, there will be a negative charge at the body, right. And we are considering that depletion region is uniform throughout this. This is only possible by maintaining now let us consider how we can use the concept of band to band tunneling to understand the gate induced drain leakage in MOSFETs. Here we are considering the simple MOSFET where this is gate terminal, this is drain terminal, and we are not showing the source terminal, because in general the source terminal is kept to 0 voltage. To have a band to band tunneling, the reverse voltage should be there and the doping should be high, then only we can talk about band to band tunneling. So, to understand this, we are just ignoring the source at this stage. Now, let us consider you apply a positive voltage at the gate. Because of this, for single positive Q charge, there will be a negative charge present in the channel. Similarly, when you increase VGB or VGS, it will deplete the surface and then it will cause inversion. That is, it is a normal operation what we have already discussed about the long channel and short channel devices. Now, take a case when you just reverse the polarity of VGS, meaning you are applying the voltage less than the flat band voltage. When you apply the negative voltage, then because of negative voltage there will be hole attracted towards the surface and there will be accumulation of the holes near the surface. As hole is the majority carrier of the substrate, there is a finite probability that here the doping concentration locally is increased, right. It means it seems like the hole concentration here locally will increase because of this voltage, meaning if the concentration of holes here is higher and the concentration of electron is higher, because it is N plus region, it forms a P plus N junction, right. And now if you apply a positive voltage at drain, then what you are doing, you are actually making a reverse bias PN junction which is heavily doped, meaning if you see the band diagram, it looks like this. So, the electron will tunnel from the filled valence band of P to the empty conduction band of the N, and hence there is a band to band tunneling takes place here. So, the hole will coming here and the electron will tunnel this side. This tunneling of electron will causes a current that is called gate induced. So, the hole will come here and the electron will go there due to tunneling. Now, there might be a case that there will be this tunnel electron will get enough energy because of this potential and there will be a electron hole pair generation, right. Because of this EHP, there will be a chance that this negative charge will deplete the N plus region locally. That what it is visible here, that this is EHPs. These electron hole pairs are generated due to tunneling and high energy. Now, because of this, the hole will attracted or move towards the body and the electron will added into the stream which is coming from the source. In this sense, which gives rise to you in the sense the gate is induces a current which is called gate induced drain leakage, meaning when you apply the enough gate voltage which causes a depletion at the drain side and there is a leakage current flows into the junction, that is what is called gate induced drain leakage. So, experimentally observed that gate induced drain leakage current is similar as the band to band current, which can be modeled by these equation where A GIDL, B GIDLs are the fitting parameter and E n max is the maximum electric field in this region. Now, if you go and put these equation in our basic equations to calculate the GIDL current, it becomes very much complex. So, we can use some simpler approach to find out the effective electric field in this region and then put back this electric field here to calculate the GIDL current. Now, how we can proceed? Let us consider that this is an overlap region, and we will write a potential balance equation in the overlap region. So, if I am interested in what is the electric field, right, here in the overlap region, it is nothing but the charge at the gate in the overlap divided by epsilon Ox, correct, which is nothing but Cox dash into psi Ox overlap divided by epsilon Ox. So, we are writing the simple equation which is Gauss's law here in the overlap region. Electric field is nothing but charge per epsilon, and charge can be written as C into voltage, right. Here this is overlap, here OV stands for overlap, correct. Now, can I write a potential balance equation here in this region? Yes, if I write VGD, because the gate to drain voltage is an effective voltage in that overlap region, right, which forms a PN junction. Now, VGD can be written as psi S overlap plus psi Ox overlap plus phi ms overlap, where phi ms is the contact potential. To move further, I can simply put back these equation here at psi Ox, correct. But first of all, I want to solve the continuity of the electric field in this region, which can be solved by writing this equation, because the electric field is discontinuous at two dissimilar material, one is oxide and one is semiconductor, right. This is nothing but drain. So, we need to rewrite this equation as epsilon S means the permittivity of semiconductor into E in Ny. So, electric field in Y direction, right. So, this is let us say drain and this is an overlap region. So, it will help you to understand like what we are doing, that we are actually calculating this E and W. The effective electric field in Y direction or the vertical direction is nothing but epsilon S into E and Y minus epsilon Ox into E Ox overlap. So, what is the effective electric field at this side is equals to Q naught dash, where Q naught dash is the charge present in the oxide, considering the oxide is non-ideal, right. So, to find out E and Y, I can use previous equations like epsilon S into E and Y is can be written as Q naught dash plus epsilon Ox into E Ox overlap, this is E. Now, Q naught dash plus epsilon Ox into this E Ox can be written as C Ox into psi Ox divided by epsilon Ox. So, C Ox dash into psi Ox dash overlap divided by epsilon Ox. This will get cancelled, you will get Q naught dash plus Cox dash common, and you can write this epsilon Ox from the potential balance equation as VGD minus psi S overlap minus phi ms overlap, which is nothing but psi Ox overlap, right. So, we will put back to this equation here as VGD minus psi S overlap minus phi ms overlap. This is nothing but what? Epsilon S into E and Y. Now, epsilon S into E and Y, you take psi Ox common and or you multiply or divide by psi Ox in both sides, you will get psi Ox dash is equals to Q naught dash by psi Ox C Ox dash plus VGD minus psi S overlap minus phi ms overlap. This quantity is known, it can be represented as flat band voltage. So, VGD minus psi s overlap minus V flat band of overlap, right. And then if we are interested in E and Y, we can simply calculate like this. So, E and Y is the vertical field in this region. Now, the effective electric field is two dimensional, because in this region the field is coming from the top as well as from the horizontal. So, you need to calculate the effective electric field, where we have only calculated the vertical electric field component, which is E and Y. Now, we need to calculate E n x. So, in simple way, E n x can be calculated as VDB divided by L effective, where VDB is the voltage between these region. This is drain and this is gate. So, the effective voltage is what this is where VB. So, where VDB is the effective voltage between drain and body, right. So, here you are applying VDB. This will give you a horizontal component of electric field, and likewise you can calculate the overall electric field, that is square root of E n x square plus E n y square. In this way we can simply calculate or model the GIDL current. If we plot the GIDL current, it is clear that due to GIDL effect the off current or the leakage current is increases. You see, if you increase VDS, the GIDL current component is increases, and that is a reverse current, right, if we plot VGS in this scale. So, let us see what are the possible leakage current we have discussed so far and how this can show in our MOSFET operation. So, to understand all the possible leakage currents which we have seen in short channel devices, we will discuss in three conditions. One is digital on condition, one is digital off condition, and one is analog operation. Meaning you are having a MOSFET, let us say this is drain, source and gate, and you are operating this MOSFET in digital on condition, right. Digital on condition means you are using this MOSFET in digital circuit and turning it on. Similarly, digital off condition means you are using this MOSFET in a digital circuit and turning it off, and in analog you are using this circuit or device, you are using this device in analog operation. So, let us see one by one and see what are the possible leakage components are present. This is a MOSFET where this is drain, this is source and this is gate. Digital on condition means what? You have drain, source and gate. So, gate is tied to VDD, means let us say you are applying 1 here and source is tied to 0 and you are taking output from drain, meaning at that stage you can consider VDS is very much small, or in this case you can consider VDS is approximately 0. So, this is the turning on condition in digital circuits, right, because you are turning on the gate by applying 1. 1 means 1 stands for logic 1, right, it is denoted by a plus VDD. So, when you do so, there will be a current, right. This current is IDS, because when you turn on the MOSFET there will be a drain to source current. Then when you apply a positive voltage at the gate, the bending will be there and hence there will be a gate current, and as the channel in the charge, as the channel charge is present throughout the channel, then this is having two component, one is IGS and one is IGD. So, this is a digital on condition. In addition to all these current, there is also a current which is due to overlap region. That is what we have discussed when we were discussing about DC gate current. Let us see the digital off operation. In digital off operation, similarly you do have 3 terminals, drain, source and gate. You are connecting gate to 0 or grounding it, right. 0 means again here logic 0, right. You are connecting 0, logic 0 is can be represented by ground. So, you are making it ground to source. Now, drain you are connecting to 1 volt or VDD volt or logic 1, right. Then and source is grounded. In that condition, you have possible leakage currents and total current coming into picture. First of all, you do have a weak inversion current flows into it, right, from drain to source. Though as we have discussed, in weak inversion also a significant amount of current flows, right, that is weak component of current. The second is there is a punch through current which can be denoted by IP. If the channel length is very small, then there is a punch through current which flows from drain to source. There is another current which is junction current, right, because drain is at higher voltage and body is at 0 voltage, we generally tie this body and source. So, there is a junction current. There is a GIDL current because of band to band tunneling, and yes, there is an overlap current which is in reverse way because you are keeping VG 0 and applying VD. This is also what we have discussed in DC gate current. There is a reverse current because the tunneling will happen from this side to that side. Now, we will discuss about analog operation. In general analog operation, you apply the positive voltage or higher voltage VDD voltage at the gate and higher voltage at the drain, right, considering body and source are tied to ground. In that condition, you do have one IDS which is major contributor of drain to source current, right. There is a junction current because drain is positive, body is 0. So, there is a junction current. There is a possibility of GIDL current. There is a possibility of hot carrier based drain to body current. So, these all components which we have discussed in previous lectures, right, and yes, there is also a possibility of overlap current, right. So, let me summarize that in this lecture we have discussed that high electric fields in the scale MOSFET increases the junction leakage, especially in short channel devices. Band to band tunneling is strongest near the drain junction because the maximum electric field present at near the drain junction. Gate induced drain leakage occurs at high drain voltage and nearly low or negative gate voltage. GIDL causes off state leakage current which is increases the standby power, right, or it increases the static consumption, static power dissipation. So, we will stop here for today. Until then, take care.